In this video, I'd like to talk about what is known as the conjugate of a complex number. And if we have some complex number, let's say we have z is a plus b times I, where I is the square root of -1, the imaginary unit, then we could say that the conjugate, which we'll write as z with a bar over it, is equal to a minus b times I. So when taking the conjugate of a complex number, you essentially negate the imaginary part. So if it was a positive number, then it becomes negative in the conjugate, or vice versa. If it started negative, then it becomes positive in the conjugate. And once you find the conjugate, these are actually conjugates of each other. So let's look at a couple quick examples. Let's say that we have z is equal to 2 plus 3i. Then the conjugate of z bar, is 2 minus 3i. But if we started with 2 minus 3i, then the conjugate of this would be 2 plus 3i. And graphically speaking, these conjugates are reflections across the real axes. So let's consider this example here where we have z1, and we can write it in terms of its real part and its imaginary part. So z1 is really just 7 plus 3 times I. And to find its conjugate, we just make the imaginary part negative. So we have 7 minus 3 times I. And in this example problem, we need to plot this complex conjugate. So we can find 7 minus 3i. It has the same real part, but now the imaginary part is negative. And you can see it's the same distance away from the real axes. Like I mentioned, it is just a reflection about that real axis. They're each 3 units away from it. And one question you might have about these complex conjugates is, why are they useful? Why should you study these? Well, if we multiply 2 conjugates together, we will always get a real number. So let's multiply these. We'll take z1, let me rewrite that. So we'll have z1 multiplied by the conjugate of z1, and we have 7 plus 3i multiplied by 7 minus 3i. And since we're multiplying these two binomials, essentially, we can use distribution. So the 7 will distribute to both, and the 3i will distribute to both. So this product is equal to 7 times 7, which is 49, and 7 times minus 3i, which would be minus 21 times I. Then we have 3i times 7, which would be plus 21 times I, and you can notice the imaginary parts are going to cancel out. And then we have positive 3i times negative 3i. Well, in terms of the coefficients on I, we would have 3 times negative 3, which would be negative 9. And then we have I times I, which we can write as I squared. And since we know that I is the square root of -1, when we square this, it cancels out the square root, and we just get -1. So I squared is -1, which we can substitute in right here. So let's simplify everything. Again, notice that the imaginary parts here cancel out. We get 49 minus 9 multiplied by -1. So that's really just 49 plus 9, which is 58. So when we multiply 2 complex conjugates together, we will always get a real number. And this has to do with the fact that we really have a difference of 2 squares here. Remember the formula for a difference of 2 squares. When we multiply a minus b times a plus b, the middle terms will cancel out, and we get a squared minus b squared. So when these are complex numbers, b in both cases would be some imaginary number, and we'll be squaring it. So we will always have I squared, which is -1, and that will make this a real number. So When we multiply conjugates, we always get a real number, and this can be useful in several applications, but the main one is division by complex numbers. So if we have an example, 3 plus 4i, and we're dividing that by, let's say, 2 minus 5i, the way to approach this problem is essentially we need to somehow make this denominator a real number so that we can have all of the imaginary numbers in the numerator. So if we multiply the top and the bottom by the conjugate of this denominator, then in the denominator, we will end up with a real number, and in the numerator, we will just have some normal complex number. And then that complex number in the numerator will be divided by whatever the real number is in the denominator. But the main idea is that this result will be some other complex number. And we won't carry out the division here, this actual process, but in a later video, we will cover exactly how to approach this. But the main idea is that the complex conjugate does have practical uses, namely when carrying out complex number division.